Okay, so what we're gonna do is I'm gonna help you isolate this site and read this code and figure out a gradient map and a site road analysis, and I'll just walk you through both the codes, very basics. Okay, so what's happening is I have this site that I got from CityWeft. It's basically measured if this is 0 and this is the meters above sea level. It basically I just split it somewhere here so that it's like little small and easier to handle. And what I did is at the top I made a polyline, and now this polyline is generally always made somewhere like below or somewhere, so it's going to be somewhere here, and then I extruded it and then basically split this to kind of get the map. I deleted everything else for now, all the extra trees and roads and buildings. So this is the site that I have. I'll isolate it for a bit, and this is a surface. Okay, you can read it and you can see that in properties you see that this is a trimmed surface. We just trimmed that whole surface. Okay, and now coming to the site gradient map, like it's a very simple uh, code. I will select all this and I'll click enable and I'll see what happens actually here. Okay, I'll hide this surface itself for a bit, and what's happening is there's this surface or a brep that let me show off like the preview, switch off the preview, and this is the surface. I put it into a mesh and I make sure that the mesh has an aspect ratio. That means each face is almost like an isosceles triangle or like a square, so the aspect ratio is 1. And the minimum edge and the maximum edge of each face is around 8 meters. So I can play this in a bit, and the mesh itself looks like this, doesn't really show any information. I need to triangulate it, again really doesn't show any information. But if I do mesh edges, this is just to visualize how my faces look like. So what this means is it's almost like these and these of every triangle are equal because of our aspect ratio, and this helps us control the mesh size. Anything too big, let's say 10 meter by 10 meter, it might not be very accurate. Anything too small, it might crash your PC. So for now I've kept it at 8 meters. You can work it out with 5 meters or 2 meters for more accuracy. Now why did I triangulate it? I triangulated it because if I directly took this mesh and just to view, we get what we call as quad faces. And what we're trying to do here is we're trying to find the slope of each of these. Now if I have a triangle, I can get the slope, whatever it is. We call this the normal, right? So if this is the overall z-axis, we can find out this normal. But a quadrilateral or a quad face, which we get right now directly by connecting this, it doesn't really define. It can be warped as well, right? It can be turned and something. So it really doesn't have a definition of a warped of a normal. So we need to triangulate it because a triangle will always geometrically have one normal. Okay, so I'm doing this. I'm triangulating it, and I need to get every face. So face normal, basically you can see the exact thing that I have a triangle there, and the triangle has an arrow. So basically that's just giving me all the normals, and the normals are basically these vectors. So if this is a face, this is a normal vector. Okay, and what I need to do is find the angle between this and this unit z. So that's what I'm doing here. I have to reverse it because it was showing 181 degree, 182 degrees. Basically it was measuring this obtuse angle, but I need an acute angle, so I just basically reverse the z-axis. And again, it's a small thing that you can ignore. The angles were in radians, so I converted into degrees, and each of these faces now have this angle. Okay, there are some 694 faces. You can see from face normals here, or the mesh information here. B387, that means 387 vertices and 695 meshes. So that means I have 695 faces, and each of them have a normal, and their normal makes the so and so degree with the vertical. So this is what we need. That means if we have a perfectly flat normal, it will make a 0 degree with the z axis, which means it's super flat, right? If this is making this with 0 with horizontal, it's making 0 angle also. Anyway, now we go ahead, we explode all of this mesh into its individual faces, and then we put it into mesh colors. And then I use this gradient. This bounds just show me the range of, it shows me the range of angles. So the flattest here is 2.3 degrees, and the most steep is 36 degrees. But what we are interested is this part. Okay, I'll just switch off this, and this is where you can play the range, and basically it highlights what range. Generally under 30-28 degrees you can build easily. Okay, so if I really want to see anything from 0 to let's say 5 degrees, you will not really probably find this super flat area, right? If you want to find really steep, let's say the maximum is 36, so 30 to 36, we'll find most of it is outside, but this is the most steep. But let's find something from 0 to 28 or 30. Now this is where you can build. This makes it understand like this is super steep, this is somewhere in the middle, and this is super flat. This is the super flat area, and this is what it is. And there's another thing, I took these numbers, rounded them off, and I put this into the tag thing, and if I switch this, you can actually find the angles. Okay, so it's super flat here, around 2 to 3 degrees, and here you can see if I change the swatch color, let's say to black, yeah, you can see that this is 18 degrees. So this is how you can quickly come to understanding the gradient. You can always bake this, make sure these are exploded mesh, so make sure to group them, and you can always take it out. And if I just do a rendered view, it does this. So very simple code that helps us get this gradient and helps us locate buildings, because you can find out the flatter areas and the not so flat and very steep areas. So that's how this thing will work, this particular code.